All right. Looks like we are live. Hello, everyone, and welcome to another Zozin session. How about that? But you didn't expect that shit to happen. So let's make a little bit of an announcement and start the stream. So let me bring up my Discord server, and the topic of today's stream is simulation mode for Porth. That's the topic of today. So red circle, well, red card. Let's use red card then. Live on Twitch and simulation mode for Porth, and we're gonna give the link to the Twitch channel, twitch.tv/Zozin, and we're gonna ping everyone who's interested to be pinged. There we go. So. For the past several, I don't know for how long, but I think for the past month, we've been actively rewriting Porth in itself. Right. So Porth, by the way, is a programming language that we've been developing for 2 months. It's moved to GitLab. So let me actually bring the GitLab thingy. So yeah, and it's come a pretty long way, I would say. So you can find the source code of this thing in the description if you're watching on YouTube, and if you're watching live, you can find the source code in the chat. I'm gonna post it in the chat. Hello everyone, hello Camel, hello Aguduk, hello Lonely Little Lucas, say hello, welcome. So yeah, the original implementation of this language was in Python. Well, it's still in Python. And we recently, like a month ago, started to rewrite it in itself. And we actually made a huge progress on that, because now the compiler is capable of compiling itself. It doesn't support everything the original compiler supports, but at least it can compile itself. One of the features the original compiler had is a simulation mode. It's more of a like interpretation mode, where instead of compiling the source code, it would interpret it. Well, it would technically compile it to basically bytecode of its intermediate representation, and then interpret that bytecode, right? So, and our Porth implementation, right? The original implementation of Porth is called Porth.py, and the new implementation is Porth. Right, the Porth implementation lacks the simulation mode. It can compile, but it can't simulate. And I decided to leave that topic for a stream. Usually I work on the compiler like off screen if there is like some very like not interesting to stream topics, like, you know, things to clean up, things to tidy up. So I usually don't stream them because it's not really that interesting to watch. I tend to stream like major features that are important for people to know. So, and yeah, one of those features is going to be the simulation mode. So let's go ahead and implement the simulation mode for Porth. Right, how about that? Hello JS Bella, hello Young Beans and Lin, Manasoima, Poly Insecure, Alex Couch, Achluara Miss, I hope I pronounced your nickname correctly. Hello, Beatstream, welcome, really glad to see you all today. How are you guys doing? Cheers, by the way. All right, so let's go. I'm gonna actually fetch the latest changes. I didn't think I actually fetched the latest stuff. I don't quite remember. Git clean fdx. Well, let me actually clean everything, and I'm gonna fetch everything. I think clean everything was a bad idea. You will know why soon. You will know why soon, because I'm not going to spoil anything, right? So I probably have to recreate that program yet again. God damn it, I forgot. I was supposed to actually commit this source code as an example to the code base of Porth, but I forgot, and now I accidentally killed it. But I mean, there is a way I can recover it, so nothing actually lost. So yeah, people already guessing what it is. It's a thumbnail generator in Porth. Right, so, and the video about that, I actually recorded that video offline, right, because it was a rather quick video. So, and it's about to actually release automatically. I scheduled it to release like in 2 hours, right? So it's going to be on the YouTube channel in 2 hours, right? God damn it. Well, I can basically recover the source code from that video anyway, and then commit it later, so that should be fine. So yeah, okay, so we have some changes in here that we probably want to merge, and let me see what's going on in here. So here's the original compiler, right? The original compiler looks like this. We can write a simple hello world. Let's actually check if our language still works, because who knows? Maybe I broke something while working on it offline. And I don't have a highlighting in Vim. Disgusting. Why don't I have a highlighting in Vim for my language? This is absolutely disgusting. All right, so I do have a support for this language, for this language in Vim. So here it is. And what I need to do, I need to copy porth.vim here, right? So this is basically where I have to copy it. So let me quickly try to do that. I'm gonna copy, so editor porth.vim into vim syntax, right? Do I even have any of these directories? Maybe I have to create them. So if I try to copy this kind of stuff, it will say that such directory does not exist. Okay, let's try to create such directory. We're going to do make dir -p, meaning that if in the path any of the directories are not present, they will be created. So basically it creates parent directories as well. There we go. So if we're going to try to copy it right now, so everything seems to be fine. All right, so now let me try to do hello.porth, right? And it still doesn't work. I think I have to do something like porth, and it still doesn't work. That's really strange. Did I copy paste it incorrectly? I think I just copy pasted incorrectly. I think I'm straight up Pepega. So what was that? And I even lost the... okay, I see. I think I'm supposed to... Okay, I'm an idiot. I should have actually created... okay, I see. I just forgot the tilde or something, right? God fucking damn it. I'm so bad at console, at Linux console. So let me now try to copy paste this entire thing. It's going to be editor porth.vim, and it's going to be vim syntax. Maybe that thing exists in there. All right, so that means I accidentally created this thing. I forgot tilde. Okay, so I just have a little bit of a performance anxiety for some reason, even though I've been streaming like for 5 years already. Right now, for whatever reason, I just have a little bit of a performance anxiety. Now, if I try to do something like this and set ft porth, yeah, finally it can highlight something. I'm not sure if it's a good highlighting, but it's at least something, right? So it's going to be hello world, right? Hello world, and then puts, and yeah. So maybe this is because it's a console vim. If I used something like gvim, it would be a little bit better. Yeah, it's a little bit better, but I cannot scale my text. Right, here we go. So we have a hello world. If I try to compile this hello world with our Python compiler, it will generate assembly, it will feed that assembly into NASM, and then it will link it to the final executable. And if you try to run it, here it is. It says hello world, but it doesn't have a new line. I keep forgetting the new line every time. So let me quickly just fix that. I have no idea why I'm using Vim, by the way, so I could have just run Emacs. I even have an Emacs running, so what's wrong with me? I don't understand. In any case, here's the hello world. So, yeah. And the rewrite of the compiler is located in porth.porth. So here is the rewrite of the compiler. It's a relatively big file, almost 3,000 lines of code, and all of that in porth. Right, let's try to compile that compiler with porth.py. Right, porth.py, I'm going to try to compile it, porth.porth, and it will take some time. Right. There we go. And if I try to run the final executable, as you can see, it created a native executable for the compiler, right? So it's not a script anymore. And if I try to run it, it basically says that you have to provide some subcommand. We can try to now compile it with itself. Right, I'm compiling the compiler with itself. And as you can see, it is successfully compiled it, with itself. Right, one of the things you can't do right now, you can't simulate it, right? If you try to simulate it, it will say that some of the operations in the simulation mode are not implemented, specifically function calls, right? So there we go. So, and here it will say that it tried to call this function, but since the function calls are not implemented in the simulation mode, it couldn't do that, right? It could not do that, and our goal would be to just like go through all of these like missing features. So we have basically a huge switch case, right? So we have intermediate representation and we have a bytecode of intermediate representation. So what we do, we just go through the bytecode of the intermediate representation, and we have a huge switch case. If the byte represents this operation, we do that. If it represents another operation, we do another thing, and so on and so forth, right? So we have a huge switch case for all of the possible operations of intermediate representation. And as you can see in the simulation mode, some of them are they're missing. So what we have to do now, we have to just try to run the simulation, and every time something fails, we have to fix it, and we have to keep repeating that until we implemented the full simulation mode. So that's basically the workflow that we're going to be using today. Does it make sense? Make sense? Hello, hello everyone. Welcome, welcome, welcome. So, does anyone have any questions maybe about what we're about to commence? Alright, so in the meantime, I'm gonna just go to the place where we're supposed to perform a call, and I suppose we need to perform the call. As far as I can understand, the call is rather simple. So the operation has the place where you have to jump the execution, and on top of that you have to save the current place, the current address of the execution into the return stack. So when you hit a return, you know where you have to jump back. Right, so we can even take a look at how it's implemented in Porsche.py. So def simulate little endian Linux, and so op type call. Right, there we go. So we have some sort of a return stack. We append the current instruction +1, so we're going to return to the next instruction after the call, and then we're just simply jumping to the address of the procedure that we're calling. So we only have two things. The problem is, in the simulation mode of Porth, we don't have a return stack, so we'll have to implement it super quick, super quick. Let me see, where is the simulation of our nation? Simulate ops. So here is the simulate ops, and here we have like a section of the code, and here we have a stack, but this is the data stack, right? It's a simulation data stack. We need some sort of a simulation return stack. That's what we need. Simulation return stack. So do I want to create like a separate capacity for such a stack? Maybe not. Right, so maybe yes. Let's actually implement separate capacity, why not? So simulation return stack capacity, and how many elements of the return stack we want to have. Usually by default I just say 1024. If we need more, I will just pre-allocate more. Okay, so the next thing we need to do, we need to allocate the memory for the return stack, right? So let's create simulation return stack, and we're gonna store U64 integers, unsigned 64 integers on it, and multiply by the capacity of the return stack. There we go. We also need to keep track of how many elements we have on the stack, right? So this is going to be simulation return stack count, size of U64. There we go. And we probably need two operations, like similar operations, like in here, simulation stack push and simulation stack pop, but for the return stack. So I might as well actually just copy paste that stuff, right? I think this is going to be the easiest thing to do. At least for now. I'm gonna just query replace sim stack, right? So this is gonna be sim red stack. There we go. Boom, boom, boom. We have to be a little bit careful because here we also have to do sim return stack, return stack overflow in the simulation mode. There we go. So that's the operation that we're going to use to push the return stack on, to push the return address onto the return stack. So we need to do the same thing for the pop, right? We need to do the same thing for the pop. I'm going to query replace sim stack, sim red stack. There we go. I don't think I have to update any capitalized constants in here, so here I can just do return stack underflow in simulation mode. There we go. So let me see if now we still compile, if we didn't make any mistakes. To be fair, I want to compile with the Python compiler because Python compiler type checks things, right? So port.port does not type check anything right now, so it's not really suitable for like serious development. But port.py is actually type checking things. Okay, so are you going to keep the compiler source in one file besides std, or will you eventually spread out different parts into different files? I have no idea. It's like asking, are you gonna use 6-letter variables in the future, or are you gonna stick with the 5-letter variables? Depends on what I need. It's just like, why is that important? Anyway, does anyone have any other questions? So we got some sort of a donation. I didn't quite see it. Something with the Streamlabs, to be fair. Just a second. So Archlua Aramis donated $5 and Z. I don't know what they are, but thank you so much for $5 and Z. Thank you for everything. I really enjoy watching your streams. All the best. Thank you. Thank you so much for the donation as well. So, will you support Shebang for using Porth as a scripting language? Here's the thing. It's not up to me to support Shebang. Right. So Shebang doesn't work like that. Essentially, I don't know who exactly interprets Shebang. Does anybody know who exactly interprets Shebang? Well, the only support that is needed from my side is probably like supporting hash sign as the comment, if that's what you mean, right? So essentially, it is not me who's interpreting Shebang. It's either shell or the kernel or something like that, right? So the only thing I need is just these things. Like, I don't have to do any special support, right? So I don't have to do any special support. Like, it's just like it's already supported, unless like but adding the hash sign as the comment is such a trivial thing that like it's literally 5 minutes. Like, why do we even have to discuss that? I don't understand the question, and I'm sorry. I think I'm being stupid. Right? It's too trivial. I don't understand. Does anyone have any questions about non-trivial features of the language? All right, so let's actually continue developing simulation. All right, so let me see. Proc simulation, simulate ops. So, all right, so we implemented the return stack, and the first thing I need to do, all right, so let's actually try to run, you know, port.port with the simulation, right? So this is going to be port.port. And the first thing I want to do, I want to grab the current IP, and I don't quite remember where the current IP is located. So is that a simulation IP? Yes, it is a simulation IP. So I can take a simulation IP, read it as a number, and then increment it by 1, right? And then I can try to push it onto the return stack. So simulation return stack. I can't see shit in this mist. Return stack push, right? So this is going to be push. We pushed it onto the return stack. After that, I need to take the simulation operation, and I need to take its operand, right? I'm taking its operand, and I need to read it as a number. So then I can save that operand as the current simulation IP. There we go. So that way, I believe, right, we push the next address to the return stack, and then we jump to the whatever address we have in the op call, right? So let's go ahead and just run this entire thing, and it still says that this thing is not implemented. This is probably because... okay, so let's actually set up the following thing. we're gonna recompile porth.porth, right? Then we're gonna run it. Right, so it will take some time, and then we're gonna try to simulate it with itself, right? That way, we're constantly recompiling the compiler and trying to simulate it with itself. So, okay, so we went past opcall, now we need to do the preparation. As far as I know, preparation is only needed for the compilation, right? So because you need to put something like switch up the stacks and prepare the return stack and stuff like that. In a simulation mode, I don't think we need to do anything in here. And in fact, in porth.py, oh yeah, this one is really interesting. So we're allocating some memory in a local memory region. All right, this is actually very interesting. Huh, that's pretty cool. So that means we need to have some sort of a local memory thingy. All right, so what's the size of the local memory that we use for this thing? Simulation local memory capacity. So we use 640 kilobytes in Python, right? 640 kilobytes in Python. So we'll probably have to use the same size, or maybe not. I don't know. We'll see. We'll see. So this is the return stack, and let's do something like simulation. Simulation local memory. Local memory capacity, right? So let's actually use 640, 1, 2, 3. There we go. So let's allocate that memory. Simulation local memory, and it's going to be just like this capacity. Usually I don't call them capacity. Usually I just call them cap, right? Because it's a little bit shorter. When you finish the compiler in Porth and remove the Python implementation, how will you distribute the compiler binary? I think I explained that multiple times throughout several videos already, and I think this is the last time I'm gonna actually explain it. So the way Porth works, it generates an assembly file, right? So we're gonna basically commit that assembly file to the repo, and if you need to bootstrap compiler, the first step you do, you compile that assembly file yourself manually with Nasm. Then you get a compiler executable, which can basically bootstrap itself after that. So I actually explained the whole process. I even remember the video where I specifically even showed, I simulated that process. Here is the video. YouTube actually listened to us. YouTube knows what is the video I'm talking about. Right. So I'm not answering that question ever again. Every time somebody asks this question, redirect them to this specific video. This is where I explained how the Porth will be distributed, how it will be bootstrapped. So I'm gonna actually put that in the description as well. So I think, let me actually see, I think I can even find a specific time code where I even showed that. Yeah, so here it is. Standard library, so I'm going to copy paste the standard library, and standard library consists of a single file, basically std.porth. Right, so roughly you're going to have these things, right, and you don't have the Porth compiler. So the first thing you would do, you would compile the porth.asm. So f64 porth.asm, right, you would generate the object file. So it will take some time. Okay, so here's the object file. We're gonna link the object file into the final executable, porth.o. There we go, and we've got the Porth compiler. Right. We can try to run that Porth compiler. Right. There we go. So here it is. And after that, with that Porth compiler, we'll be able to recompile it with itself. And there we go. So we just bootstrap the compiler. Right. So this is roughly how this is roughly the workflow that you're gonna have in the future for this specific project when we get rid of the Python. Okay, so I think it's a pretty good explanation, in my opinion. So I think I need to even save the time code, right? So Right, so roughly you can...
So it's around...
consist of a single file, basically std.port. Right.
So, and what's cool about YouTube... What's cool about YouTube is that you can right-click this thing. You can right-click and copy a video URL at the current time, right? So, and you get a URL that you can just, like, you know, share with somebody. So I'm gonna go and just put this in the description. How Porth is going to be bootstrapped after complete removal of Python, and here is the link. So do we have something like a bootstrap command? Let me actually see. Bootstrap. We don't have. I'm gonna create the command @cmd bootstrap, right? So I'm gonna put this link in here. So every time somebody asks how you're gonna bootstrap the compiler without Python, give them this specific link, please. Okay, thank you very much. Cool. So Cozy White Bear, thank you so much for 11 months of Twitch Prime subscription. Thank you. Did I fuck it up? Okay, so it's fine. Thank you, and welcome to our Epic Porth Club. All right. So I think everything's okay. All right, so let's continue. So I'm gonna save the description. I'm gonna save the description. All right, so this is the simulation local memory or something like that. So we also need to allocate some sort of a variable that keeps track of the RSP, basically the top of the stack. So essentially, in terms of the local memory, in a simulation mode, we just grow the local memory towards the 0, the similar way x86-64 works, because it just like makes it similar, makes it easier to keep the environment consistent between the compilation mode and the simulation mode, right? So that's why we need like an extra variable to keep track of this kind of stuff. Okay, memory simulation local memory RSP size of U64. So here is that, but when we start the simulation, we have to initialize the RSP with the value. We basically have to set it to simulation local memory capacity. Right, so let me actually see. Yep. But to be fair, we actually have to set it to simulation local memory plus the simulation local memory capacity, because this thing is supposed to be a pointer. That's right, so this is actually a pretty cool idea. So it has to be a pointer. So we get this value, then we take simulation local memory RSP and we save that pointer there we go. So now we keep track of the RSP pointer. It's a pointer that points at the top of the stack. Okay. So we need to go into the preparation procedure. All right. And in here, so the cool thing is that I can always look into the Python implementation and just steal something from there. OP type. OP preparation. Is it OP? It's actually not prefixed with a P. Prep. Yeah, there we go. So essentially I need to take the operand of the current operation. So I have to do sim op operand, right? And I have to read it. So here is the operand. Then I have to subtract that operand from RSP. So that means I have to take the local, actually simulation local memory RSP. I have to read it as well. There we go. So here is that value, here is the second value, and I subtract this value from that one, and I have to save that value back
into RSP, right? I have to save that value back into RSP like so. But here's an interesting thing. I want to have some sort of a check. And you want to have some sort of a check that this thing does not sort of overflow the local memory stack, if you know what I'm talking about. So I think this is the only place where we're gonna like allocate this kind of memory. So I'm not gonna extract this into a separate procedure because of that. So I think I can put that check right here. So essentially if, not really here, simulation local memory capacity RSP, I can read that value, right? I'm reading that value. And then I need to compare it with the simulation local memory. And if, for whatever reason, this thing becomes less than this one, actually we have to read this one as a pointer, right? So it stores the pointer, and this thing is also the pointer. If at any point the top of the stack becomes like lower than the beginning of the memory, that means we hit an overflow, right? So, and let me actually print an error for specifically for that error. So local memory capacity exceeded in the simulation mode. It's kind of interesting, right? In the compilation, we use return stack for both return addresses and the local memories. But in the simulation mode, for whatever reason, I decided to actually separate those addresses. I don't have any specific technical reason to do that. It's just like it was easier to do that. All right. So it was just easier to do that. Okay. So, and in here I probably want to exit with like non-zero exit code in case this kind of stuff has happened. Alright, so maybe I also want to show where exactly this error has happened, right? Because we know we have an operand, right? We have an operand, and inside of the operand we have a token, right? So I can do simop. I can take the token from which the operation has originated, and then from that token I can extract its location, right? And I can print that location to the standard output, right? Like this. And then I can say this happened like here. Note the error has happened here, right? And then we're gonna do it like this. All right. So looks good. So we pre-allocated some memory, and then after that, prep proc, right? Prep proc. We just go to the next instruction, right? So we just simply increment the simip. Hopefully that will work. Hopefully that will work. Okay, so let me try to compile. Well, I mean, okay, so I want you to compile that. argv is not implemented. Wow. Oh shit. Okay. All right. This is actually pretty interesting. So do I really want to jump into like argv right away? Maybe we should try to simulate like simpler program first, right? So let's not try to simulate the compiler itself. In the examples, we have a lot of like different programs like bubble sort, cat, checkers, Fibonacci. I think we even have hello. Yeah. So let's actually start with the hello world, right? Let's try to simulate hello world first. Because simulating the compiler itself, it could be actually a little bit overwhelming. So hello world. Okay. Alright, so now we need to implement push str. So here we just have to push the pointer to the string. So what's interesting is that the operand inside of this operation contains an index in the array of string literals, right? Str lit. Where is that array? So I think it's somewhere in begin str lit. Is it a string?
Where is it? I don't see it. Begin str, and it's missing. So there is a str buff. Okay, so there is a str buff, but where is str lit? See str lit. Oh, because it's capitalized. Right, Emacs for whatever reason couldn't find str lit because it was capitalized. I thought it has a like case insensitive search. Anyway, so essentially the operation of pushing a pointer on the stack, pushing a string on the stack, contains an index inside of this array. So essentially what we have to do, we have to take that index and get the string literal by that index. Right. And then we have to push that onto the stack. So let's go ahead and do that. So this is located here, and this is what we're trying to do. Okay, that's cool. So I'm gonna take this simulation OP operand. Here is the operand, we read it, and we got the index, right? So then I need to multiply it by the size of the string, because the array of string literals contains strings, right? So that's why I need to multiply it by that. And then I can need to take str lit, I think it's called str lits, right? And I add this thing, and now on the top of the stack, I have a pointer that points at the element inside of that array. So here it is. Here's the element inside of that array. So, and now I just have to... This one is interesting, right? I have to put that string onto the stack, right? After I put that string onto the stack, I have a pointer to the beginning of the string and the size of the string. So now I have to take these two values and push them into the simulation stack, right? So it's quite interesting. So I have my own data stack, and I also have a simulation stack of the program I'm simulating. Right, so that's actually very interesting. I suppose, like, and if I just do something like simulation stack push, right, that will push a pointer onto the stack, on the simulation stack, and then it will push the integer, right, and it will work. Now we don't even have anything. Wait a second, it doesn't accept. Oh shit. Okay, so the simulation stack actually accepts only integers, not the pointers. So before you can do that, before you can push the pointer, right, you have to cast it to integer, right? So let's actually cast it to integer. There we go. So as you can see now, we consumed all of these things. But when you pop elements from the stack and push them into the other stack, they will be pushed in a different order. So what we have to do before pushing them, I think we have to swap them, right? So in here, we'll have the order of pointer integer, right? But before doing that, we can swap them, and now it has integer pointer, and then we're pushing them into the simulation stack, and there we go, we consumed our, well, and because of that, I have to cast it in a different place. There we go. Okay, that's pretty cool. So for those who doesn't know, this is a special operation. I think it's just like a stop operation. Basically, what it does, it instructs the compiler to stop the compilation here and show the current type stack, the stack that it uses for type checking. Right, so, and it's actually very convenient for like inspecting the program. Like at any point of the program, you can just say, what is the state of the stack here? Can you tell me what's going to be the state of the stack here without actually executing it? Just show me the types and where they originate, and it will stop the compilation and will just tell you, which is rather convenient. Right, so it's basically says, okay, so at this point on the stack, you only have an integer, and that integer was pushed by this operation. Well, it originates from the multiplication. Right, so you can now put this thing in here, and as you can see, before the multiplication, you had two integers, and you can see where those integers are coming from. So this integer comes from a read operation from the memory, and this integer comes from this thing. So basically, by you know, placing these question marks, you can trace different datas and different like you know, execution paths, which is rather convenient. I think it's a pretty cool invention that they came up with. Forth doesn't have anything like that, right? So as far as I know, in Forth, there is really weird philosophy in Forth, is that if you need any tools to debug or inspect or analyze your code in Forth, your code is bad.
Something like that. And somehow that justifies not having static typing, not having a debugger, not having like any tools that help you to analyze this thing. It's really weird. Like, I briefly looked into the philosophy of Forth and it was really weird. Right. So if you need any tools that actually help you as the developer, your code is bad and you should feel bad, you should throw it away. And that justifies not doing anything. Well, I guess it's some definition of a bad code. So I've seen worse definitions of bad code throughout my career, but it still sounds really weird to me. Maybe I misunderstood something, right? Maybe somebody could enlighten me on the Forth philosophy, but I couldn't understand that. Did I make a confusing programming language due to the dynamic typing? No, it's the programmer who's wrong. Exactly. Alrighty, so I think this is fine now. Right. This looks readable. Look at that. Concatenative languages were a very good idea. This is absolutely readable. I love it. Anyways, so let's actually try to run it once again. Okay, so this thing is still not implemented. Push it. Wait. What did I implement then? Wait a second. Did I really implement sister? I don't remember implementing sister, excuse me. Alright. Okay, so I think I actually missed a little bit and I implemented... Okay, so sister is supposed to be implemented slightly differently. Okay, the implementation has to go there. Alright, I'm really glad that I have like extensive amount of checks that constantly crash the compiler and stuff like that, because it saves my ass so many times. Okay, so I think this should actually go here. Okay, data stack overflow in a simulation mode. Cool. I think this is a classic. Who can guess what I forgot? Who can guess what I forgot? Any OGs in the chat who were actually following the development since the beginning? What did I forget? IP+1, exactly. I forgot IP+1. So here's the thing, like IP+1 is such a simple problem. You just do IP+1 at the end of the iteration, right? At the end of the iteration. But you have to do IP+1 in each of the branch of the switch case, in a switch case, unless you don't. So there is like a 5 or 6 branches where you don't have to do that. And it's just like, I don't know. So, and it's kind of weird, not gonna lie. So let's go into the proc simulate ops op push str. OP push str, and in here I suppose I have to do this thing, right? So I increment the simulation IP, and I also have to, yeah, okay, so in the preparation I also increment it. Okay, syscall 3. Oh my god, our simulation mode tried to call a syscall. Holy shit. And unlike in Python, this is actually super easy to implement in here, right? So essentially we have to just use the syscall 3, you know, intrinsic, right? So basically in the simulation mode, we can just reuse the intrinsic of the language itself, of the language that we're simulating. And that way simulation will be able to do all of the things the compilation can. Which is kind of cool, and it's probably going to be even like as fast as the compilation. Maybe not. No, it's not going to be as fast. It's going to be like a little bit of the overhead of simulating everything and stuff like that, but it's definitely going to be faster than the Python simulation, that's for sure. That's for freaking sure. Zelen Zero, hello, welcome to the stream. So okay, So let me see how we're gonna do that. Here is an interesting thing. So essentially, syscall3 accepts 4 arguments, right? It's kind of counterintuitive, but it does accept 4 arguments. So first 3 are the arguments of the syscall, and the fourth one is the syscall number, right? So yeah. So, and even syscall 0 accepts at least 1 argument because it accepts the number of the syscall. Was the name Porth inspired from porn? Yes, the answer is yes. So this is the official lore. This is the canon. Porth comes from porn. Anyway, so syscall. What we need to do. So we have 4 arguments on the stack. We have 4 arguments on the stack. We have to move those arguments from the simulation stack into the data stack and just call syscall3. Right, we can do something like sim stack pop, right, and we have to do that 4 times. Right, we're doing that 4 times. But we can't just do syscall3. We can't just do that. Because in the simulation stack, they are in one order. And then once we pop them into the data stack, they're going to be in a reversed order. Right, so, and I'm not even sure how we can sort of reverse them. Let me see. So in the simulation stack, right, it's going to be A1, A2, A3, and then the number. Right, so this is how they're going to be in the simulation stack, sim stack. Right, and then data stack, my data stack. Once I start doing pops, so I will pop number first, so here goes the number, then A3, then A2, then A1. There we go. So, and I can't call syscall3 on that because like this is not a correct argument. So I need to somehow reversal of that. I wonder if there is any way where I can just actively reverse things, like actively keep reversing things, but I don't think so. I don't think I can easily do that. Maybe we'll have to introduce some sort of like a third stack. Maybe. It actually depends. I have an interesting idea. So we don't have an arbitrary access to our own data stack. But we do have an arbitrary access to the simulation stack because the simulation stack is just like a region of memory where we can access things at random. What we can do here, instead of using simulation stack pop, we can directly get the elements from the simulation stack and put them in the whatever order we need, right? So I think that would be a great solution that will scale to even 6 arguments, right? Basically check if you have enough arguments on the simulation stack and get those elements directly from the stack. Just directly get them and then just pop them out of the stack or something like that. Okay, so I'm thinking maybe we could implement some sort of like a simulation stack operation which accepts how many arguments do you want to pop off this stack and map them into the data set. This is actually a pretty cool idea, actually. God damn it, our type system won't allow us to do that. Fuck. Right. So I won't be able to create the procedure that will return a variable amount of the arguments based on the input, right? So here's the thing. So Porth, what I want you, so the thing that I want to do requires the following thing: simulation stack, I don't know, pop, and it will accept an integer, and it will return the variable amount of integers based on the input. If the input was 5, there's going to be 5 of these things in here. Our type system isn't capable of doing that yet. In the future, we're going to have a lot of interesting things about variadic input arguments and variadic output arguments. We're going to do all sorts of things that can be checked at compile time once we re-implement everything in Porth, of course. But for now, we have to live with a very simple and very dumb type system. So just saying. So I think I want to make a small break because I need to refill my water. And after the break, we're going to continue and we're going to try to implement this thing where we can just like take three elements from the simulation stack and put them in the same order onto the data stack. So then we can do the syscall 3, right? And whatever we developed for that will be useful for syscall 4, syscall 5, syscall 6, and so on and so forth, right? Does that make sense? All right, let's make a small break. All right, so let's continue. Let me think how we can access all of those elements. All right, so simulation stack pop. I need to find the procedure simulation stack pop. Right, here it is. So here we take the count, and count points to the element after this entire stuff, right? So this is essentially how we have it. A, B, C, D, and count points somewhere here, right? If I subtract 1, I get that argument. So we got some subscription. Claw76 subscribed for 5 months with tier 1 subscription. Thank you, thank you, thank you, and welcome back to our Epic Port Club. Thank you, really appreciate it. All right, so now let me think. So if I do -1, I will access this one. So essentially what I need to do, I need to do -4, and if I push this thing, I'll push it. Yeah, so essentially I have to start with -4 and push the elements, like start going forward or something. So simulation stack. But before I can do that, I need to check that I have enough, you know, elements on the stack in the first place. Right, so the first thing we want to do, we want to take a simulation stack count, we want to read it, and we want to check that we have at least 4 elements there. So this is going to be 4, greater or equal, right? Actually, if it's less than 4, we're going to say the data stack underflow in the simulation mode. That's basically what we're going to say. Data stack underflow in the simulation mode. Yeah, that's fine. I was still thinking maybe I can come up with a better solution, but I didn't really see it. Okay, so this simulation underflow. All right. So, and in here, what I have to do is just like I have to take this thing, 64, and then I have to subtract 4. If I subtract 1, I get that one, 1, 2, 3, 4, so I just have to do 4 minus. Then I have to multiply this entire thing by the size of the element of that stack. So this, I need to find memory simulation stack. Right, the elements have the size of U64, so I have to multiply it by U64. And then I have to add the simulation stack in here. So that way I get the elements in here. And then I just read that thing, right? So then I just read that thing. Interestingly enough, right, I can sort of like straighten it up and duplicate this entire thing 4 times, right? So, and then I can switch these elements. So here I'm copying the 4th element from the simulation stack on the top, then the 3rd one, and then the 2nd one, and then the 1st one, and they will come out at the correct order, hopefully. Yeah, that's basically how we're gonna do that. So after that, after that, I will perform the syscall, right? And the syscall will essentially return. The syscall will essentially return the code, the return code from the kernel. So before I can do that, I need to remove all of these 4 elements from the simulation stack, and I think I'm going to do it like this. So it's going to be simulation stack drop, and we're going to also drop it like that. 1, 2, 3, 4, right? And also let's delete training white spaces. Okay, and then I will be able to push the return thing into the simulation stack. Right, let me actually double check. So here we should have only a single element on the stack, or at least on the top of the stack we should have whatever we returned for, whatever we got from syscall 3. Okay,
So this one should be called pop, right? This one should be called pop. And as you can see on the top of the stack, we only have an integer that originates from syscall 3, right? So, and the only thing we can do with that thing is just like push it into the simulation stack, right? So, and that's pretty much it, I think. All right. So I think it performed this simulation. Look at that. It already performed the syscall, but it still failed because we didn't remove this, this assertion, right? So essentially, I think it works. I think our port compiler is capable of interpreting hello world. How about that? So that's actually pretty cool. Almost. It managed to print hello world, right? But then it needed to return from the procedure that printed it, right? So it actually went into the right syscall, which performed the syscall 3, but now it had to perform the AND. IP+1, yeah, thank you for reminding me about IP+1, that's right. So let's not forget IP+1, increment 64, there we go. So this is the way we're gonna implement the syscalls. I think it kind of makes sense to actually put the drops somewhere here, if that makes any sense. Oh my god, what the fuck is going on? Emacs is going freaking crazy. Okay, so let me delete trailing white spaces. And what I wanted to say, yeah, so essentially we're gonna get those things from the stack, we're gonna pop them right away, and then we're gonna call the syscall, and then we're gonna push the result of the syscall onto the stack, onto the simulation stack. All right, so and then we can copy paste like a similar solution to all of the syscall implementations. I think it's going to be pretty straightforward. Anyways, so let me recompile it one more time. And something went horribly wrong. What did I do wrong? What did I do wrong? Yeah, okay. So I should have actually dropped those things, right? You have to drop them right away because pop actually pushes it onto the data stack. All right, so, and so that's really funny. Return stack on the flow. All right, so what is going on? Holy shit. Am I going crazy? What the fuck is going on? So I did IP+1, then OP return. Where is OP return? Let me actually find that, because it's supposed to, I think I accidentally removed it or something already. Oh boy, OP return. Right, it's supposed to exit when it tries to return, but it kept doing this thing, and syscall 3, where is the syscall 3? We do increment this thing, right, so everything should be fine. Is that because I moved this thing before the syscall? Is that what's happened? I don't quite understand. Why does it act like that? So I made a small mistake, and now it just like keeps doing this stuff, and I don't understand why. Did it accidentally remove the... Oh my god. I think like I pressed something in Emacs, and it deleted something that it's not supposed to delete, and now I don't know where it is, so I have to look at the diff. Just to see what the hell is going on. Alright, so here is this kind of stuff. So here is the sim IP +1. And in a call it's supposed to have sim. Okay, so I think it removed sim IP. Did it even have one? I don't remember if I actually incremented the instruction pointer at the call. Well, it's not supposed to do that. Why is it keep repeating? I'm so confused. It's like, what did I do wrong? And so I also get messaged right now. So, all right. So let me see. Oh boy, I love software development. So what is going on? Why is it keep repeating this thing? It's not supposed to keep repeating it, right? It is not supposed to keep repeating it. So if I put something like here, to do blurb, right? To do blurb eputs, right? Eputs 1 exit. Oh boy. All right. So let me see. Okay, so here is the blurb. It didn't really do that properly. Okay, so then so we did one hello world, and after that it will probably go, right, it will probably go into the OP return, right, it will probably go into the OP return, and in OP return, where is OP return? I don't see it. Let's find OP return. In OP return, it's supposed to fail, but it didn't. Syscall. Instead of doing that, it keeps repeating hello world. Right, until return stack overflow in the simulation, until return stack overflows. So it keeps calling that thing. So I'm so confused. Okay, so syscall 3. And what's funny is that it just worked and it failed at the OP return. We saw that like a minute ago or something, like several minutes ago, and then I just switched something around in here because I wanted to restructure things, and it stopped working, and I don't understand why. Like it failed at the right place. It should fail at OP return, but now it doesn't. This is so weird, and I don't understand. It's just like it's not supposed to do that. So, like, where did I forget shit? Okay, so in a push string, okay, I do see my IP. In a preparation, I increment everything. In the syscall, I increment everything. In a call, I'm not supposed to increment everything, anything, because we're supposed to jump into that thing. Right, we're supposed to jump there. But we keep jumping there, like... Alright, so let me actually remove this entire thing. Right, so I'm gonna just go ahead and remove this implementation. Right, so we're gonna start over, almost like kind of start over, and then we'll see what's going on. All right. Okay, so it fails at syscall 3. That makes sense, right? So that makes sense. We're starting over. Then I'm taking the simulation stack. Simulation stack count. All right, I'm reading this entire thing, so this is going to be 64, and I'm just checking that this thing has at least 4. If it has less than 4, right, so I have to do the following thing here. So sim stack pop, right, so I have to fail with this thing in here. I have to fail with this thing in here. So here is the simulation mode. Cool. Then I take the simulation stack count. I read this entire thing, right? So I'm just reading this stuff. Then I'm subtracting 4, right? I'm just subtracting 4. After that, I want to multiply it by the size of this thing, and I'm gonna add the sim stack here, right? So that's the pointer that I want to try to achieve, and here I'm reading this thing yet again. Okay, so that makes sense, I think, right? And I'm gonna do that 4 times, so this is gonna be 3, 2, 1. And if I take a look at what we have in here, right, we have 4 integers that we got from the simulation stack, right? So all of them are in here, right? All of them are in here. So then I want to perform the syscall 3, and the syscall 3 actually returns that integer in here. Okay, so the next thing I want to do simulation stack pop, and I'm gonna drop it 4 times. Right, so after that I'm still gonna have that you know, integer, and then I'm gonna do sim stack push, right, and I'm gonna have no any elements on this stack. So then I can simply do simulation IP increment 64. So I just recreated the entire thing. It should say hello world 1 and hello world, and then it will fail in here. So now if I remove this thing, did it hit return or did it not? Did it hit return or did it not? I'm extremely confused. I can just go ahead and implement the return, I suppose. But it's so weird. Like, what the hell? So why does it not hit the return? Why it does not hit the return? Can we trace the operations somehow? So it keeps repeating everything. Why would it keep repeating? So if I remove this thing, if I don't increment the IP, it hits the return. And it hits it in here. Who increments the IP? What the fuck is going on? Excuse me? What is going on? Like, why? Syscall 3, right? What? It doesn't make any sense. I don't understand. Like, why you don't have to increment it? You have to increment it, don't you? I just played myself. I hate that IP+1 problem. I absolutely hate IP+1 problem. Okay, so here's the thing. In the intermediate representation, we have operations, different kinds of operations. Okay, so let me actually show you these operations. It's so dumb. Holy shit, the entire problem was extremely dumb. So here are all of the possible operations of the intermediate representation. You can push an integer, push the local memory, global memory, strings, if, else's, blah, blah, blah. And one of the operations that you can have is intrinsic. An intrinsic is basically a hard-coded function.
So here's this thing. Intrinsics by definition don't change the control flow of the execution. So because of that, they never have a situation when they directly assign IP. So for any intrinsic, once you executed the intrinsic, you can just increment by 1. And because of that, for the intrinsics, I actually moved IP plus 1 outside of the huge switch case. And yeah, so basically you have to do IP plus 1 for each branch of the switch case, unless you don't, and for the special operations you never have to do that. It would have been better, I think at this point, it would have been better if I just like updated IP on each individual branch regardless of something being compressible or not. Right. Regardless of something being compressible. So, yeah. Alright, so I have to... It doesn't really matter, whatever. But it's so annoying. This is such an annoying problem. Like, it produces the code that is not compressible. It's a, like... Right, because you always have to do that unless you don't. Right, and it's always like that, right? So usually you may think that a particular repetitive code is easy to abstract away. But it's always, like every instance of the copy-paste code is slightly different. It's just like slightly a little bit different, and it makes it almost impossible to abstract it away, and you just have to copy-paste it. So not all of the code is easily compressible. And this is something that you have to deal with like all the time. Right, and since the CS grad students are so afraid of duplicate codes, when they encounter this situation when you have to duplicate code but slightly differently, they get stuck because the professor told them that you're not supposed to copy-paste, but in the wild, you're expected to copy-paste, and they don't even know what to do. Like the professor says one thing and the industry says another thing, and that's how they get stuck. Right. And it takes years and years of the experience to actually get unstuck from that mindset that you're not allowed to copy-paste and actually start fucking copy-pasting things and getting shit done. So it took me like 10 years to actually get to that point. It's really difficult. Right. It took me 10 years to get rid of the fear of copy-paste. Imagine that. That's how long it took me, right? Because for the 10 years I was afraid to copy-paste code, because the code has to be compressed. Don't repeat yourself. Keep it simple, stupid. Don't repeat yourself, and other like hundreds of other like, you know, solid-like abbreviations. And it takes so much effort to get rid of that mindset and finally start doing things. All right. So anyway, so you don't have to do that thing in here, and yeah, I'll have to keep that in mind. So here are the intrinsics, and so here's the OP. I don't even know where the intrinsics start. Okay, so here's where they start, and then okay. Now let's go. So it should fail at OP return, right? Okay, so let's go ahead and implement OP return. OP return, OP type return. So here we just have to take the local memory RSP and add the operand, right? So local memory, it's actually simulation local memory RSP. We're reading this entire thing. Then we take in the operand, OP, it's actually simulation OP operand, right? And I'm reading that thing, and I'm summing things up, and then I'm saving the result back into this variable, right? I'm saving this entire stuff back into the variable. All right, so that way I deallocated all of the local variables in here. So the next thing we want to do, we want to pop the element from the return stack. So it's going to be simulation return stack. And then I want to assign that value into the simulation stack. Right, there we go. So that's how we're going to do all of that. And is it going to work? Is it going to work now, yo? Look at that. We simulated Hello World. Look at that. So now I can do that without intermediate recompilation or something like that. I can just take the Porth compiler and go ahead and try to simulate hello world. And I couldn't do that because I forgot the subcommand. There we go. So as you can see, here is the simulation of hello world. Right, we're basically interpreting it. So, and it takes us 64 milliseconds to simulate that with the Porth. And if we compare it with Python, it takes 200 milliseconds. Almost 200 milliseconds. So this is the Python simulation and this is the Porth simulation, which is 4 times faster, almost. A little bit less than 4 times, but I mean, it is faster. What's interesting is that I didn't do any optimizations to the Porth implementation. I didn't optimize anything. And you're gonna be shocked. You're gonna be shocked right now. I'm gonna tell you like a little secret that I didn't tell anyone, and I implemented all of that off screen so people don't yell at me while implementing that. And so it's very important for me because otherwise I won't get any shit done. So essentially in the language we have to have tables that map a name to a particular entity because we have a lot of constants, right? So for instance, if you go into the standard library, there is a shit ton of constants, there's a shit ton of procedures and stuff like that. And to keep track of all of that, you need a table that maps a name of the constant or name of the procedure to, you know, its metadata. You know what data structure I used for these tables? You would think that I used a hash table. No, I used a linear array. So when I look up a name, I look it up linearly 1 by fucking 1. 1 by fucking y. And this shit is still faster than Python. It's still faster than Python. I'm using the wrong data structure and this thing is faster than Python. So imagine how fast this motherfucker is going to be when we switch to hash tables. I'm gonna do it like a separate stream where we implement a hash table in Porth. We implement a hash table in Porth and we'll measure how much this thing will speed up. All right. It's called associative arrays. Okay, so you can use whatever name you want. Don't want to be toxic, but is that really such a big achievement being faster than Python? Yeah, you're right. I'm just like making fun of Python at this point. Yeah, you're right. It's not that big of an achievement. I do agree with you. So it is true. So yeah, anyway. So let's actually commit whatever we have already. Porth.porth make how can we say that? Porth simulation mode can simulate hello world, hello.porth examples hello.porth, right? So it now can simulate that. I'm gonna push that right into the repo. You can find the source code in here, and then let me see. So if you're watching on YouTube, you can find the source code in the description. Alrighty, so let's go ahead and pick a different example that we want to simulate. So what's going to be the next thing we could simulate? I think we could simulate name, right? It's actually a pretty cool program. So if you do something like porth simulate example name.porth, right? It asks for your name. You say your name is Alexei, and it says hello Alexei, right? So if you try to simulate this entire thing with porth.porth, it will fail, saying that, yeah, this thing needs to be able to push global memory, right? So let me think. So that means we'll have to allocate global memory stuff or something. Oof. This one's gonna be interesting. Porth.porth. So let me go ahead and do that thing.
Pors.py compile pors.pors. Pors.pors, and then if I'm gonna run this entire thing and I want to simulate examples name.pors. Do I really want to use the compilation mode? I'm not sure, because the compilation mode does not allow you to enter the values. So, but maybe that's fine, because I'm gonna just go through the errors and just fix them one by one. Okay, that's actually really funny, right? What is your name? It managed to print what is your name, right? But then it couldn't, you know, push the global memory or something. So it's kind of funny. This is not what I wanted. There we go. So global mem, push the global mem. So for the global memory, we'll have to just like have a buffer for the global memory. So the most logical thing would be to dynamically allocate the global memory, because after the compilation, right, global memory capacity, right, after you compiled the program into intermediate representation, right, after you did that, this variable holds how much of the global memory is expected for your specific program, right? So basically, before the simulation, what we have to do, we have to allocate the buffer of this specific size, basically malloc it. But I'm thinking, I don't want to implement malloc right now, and I don't want to mess with mmap right now. Do I want to do that? So I'm basically going to pre-allocate like a fixed buffer. Ah, shit, it's not going to work. It's not going to work because we're allocating a lot of like global memory and stuff. So we probably have to call mmap. Ah, shit. Okay. So that's probably what we have to do. All right. So let's allocate a little bit of memory using mmap. Does it sound good? Sounds Gucci? Sounds Tamaguchi? Let's go. So proc simulate ops. So here we're gonna have memory sim global memory, and we're gonna basically store a single pointer in here, right? We're storing a single pointer, and we're gonna obtain that pointer by actually calling mmap, right? So let's go ahead and do that. Man mmap. I don't remember how to allocate memory with mmap, but I'm gonna try to remember. So here we are initializing the like local memory for the simulation, and here we'll have to initialize the global one. So first thing we have to provide is an address, then the length, then the protection, then the flags, FD. I don't remember what kind of FD you have to provide if you are basically allocating memory, but we'll see. Okay, so address. We don't know where we're gonna allocate the memory, so I'm gonna just put null in here, right, and it will just choose that for us. So the length, right, we know the length. It's a global memory capacity, right? So after the compilation, the expected global memory for the program is located in here, so we're gonna just use that. So in terms of protection, basically tells what you can do with it, with the memory, read, write, and stuff like that. So it's gonna be prot, yeah, read, write. So I think this is the only thing we need from the memory. So I'm gonna do something like prot read, prot write, and I'm gonna OR them into a single mask. So in terms of flags, I don't remember what kind of flags we need to have. So private, create a private copy and write updates to the mapping are not visible to the other processes. I think we'll need map private at least. And another thing we'll need, I actually don't like to remove this thing. Another thing we'll need is probably map anonymous, right? Map anonymous. So the mapping is not backed by any file, and that's precisely what we have in here, right? So, and we're gonna OR this entire thing. So in case of FD, okay, so FD argument is ignored. However, some implementations require FD to be -1.
Okay, so here's an interesting thing. Porth.porth right now does not support like negative numbers properly. So if I want to have -1 in here, I have to do it like that. Right, so this is called the art of getting shit done. Right. Look, people, I implemented a self-hosted compiler without negative numbers. This is the art of getting shit done. Right? Don't judge me, because I get shit done. Anyways, so the offset, I suppose the offset is going to be 0. There we go. Right. While you're constantly rat-holing over what kind of syntax you want to use, what kind of keyword you want to use for your procedures, is it going to be proc, is it going to be func, is it going to be fun, is it going to be something else? While you're discussing all of that, I'm getting shit done without negative numbers. So the same. And it's not that hard. Weird flex. Exactly, it is supposed to be a weird flex. It is supposed to be, because it's not a flex. The point of what I just said is not a flex, because anyone can do that if you just stop bike shedding. You can do so much if you just stop bike shedding and focus on what's important. It's not it's not meant to be a flex, because it's not just like I'm God coder or something like that. Anyone can do that. It's just like stop bike shedding. And for those who doesn't know, bike shedding is a pretty important term that you have to learn when you're doing software development. Right. So if you never heard about law of triviality, Jesus Christ, I don't know how to speak English. I really recommend to check it out. So yeah, check it out. It's really cool. All right, I'm gonna put that thing in the description as well. And yeah, it's not supposed to be a flex, because anyone can do that. It's not a flex. You just have to believe in yourself. Just have to believe in yourself. Alrighty. Hopefully that's it. I think we'll have to define some of these constants, probably, right? To stop watching, start streaming. Everyone can do that. Exactly. And after that, I'm going to do sim global memory, and then I'm going to save it in here. So what's interesting is that this operation can fail. So we probably want to check, right, if it didn't fail. So global memory, we're going to read that thing, and map failed. If it's equal to map failed, we're going to say something right here. Error could not allocate. So, and I think we have to do it like this, right? So this is going to be eputs. Eputs could not allocate global memory capacity. Global memory capacity 64. Eputs u bytes for of global memory for the simulation. Eputs, and then we're gonna do it like that. So, by the way, but that doesn't mean that you never have to implement negative numbers. That doesn't mean that if you ignore some trivial problems for now, you never have to go back to them. You eventually have to go back to them and fix them, right? So I'm just currently trying to get to the point where, you know, it's mostly done. Right, and once it's mostly done, where it's at the right point, we can start to, you know, cleaning things up and tidying things up, and implementing all of these like missing features and whatnot, right? So it's more of a like a, again, like I'm comparing that with the illustration, right? When you draw an illustration, you start with a sketch, with a rough sketch, which is not finished, which doesn't even look like a final illustration that you're going for, but it just gets the shape right. And then you start the line work, right? So you line over your sketch, then you fill in the colors, right? Solid colors, and then you like cell shade it, or just like some kind of a shading, and like gradually, slowly you bring the illustration together, right? So you don't try to draw it right away. Usually you start with the sketch, and it's the same thing with the programming. Actually, it's the same thing, right? All right, so unknown word prot write. All right, let's take a look at the standard library. Prot. We have a prot read, but do we have a prot write? And what prot write is supposed to be? So let's actually try to find it in here. Okay, so I'm gonna grab rn define prot write. So it is defined somewhere here. So prot write is supposed to be 2. It's libr, it's a radare. I see. std porth. So lib or write is supposed to be 2. And then we also have to do anonymous, right? Anonymous is actually 20. Is that the correct thing in here? So private is 2. Private is 2 here as well. Anonymous is 20. Okay, so it's gonna be map anonymous. And 20 in hex. I'm not quite sure what is 20 in hex. 32. All right. 32. I don't know hex by heart. I'm sorry. I'm not a god cooler. So let's continue. Okay, so let's try to compile the entire thing. Okay, unknown word map failed. I do remember actually creating map failed. Oh, it does not exist. Okay. Well, it's kind of weird. Why do I remember actually creating map failed? So map failed, it's basically -1, but oh, I do remember why. I do kind of remember why. Because it's a negative value, right? So, but we can quite easily do the following thing, right? So let me go to the porth. Right, and basically I'm gonna put null, and if this entire thing, for whatever reason, is less than null, that means we couldn't allocate this entire stuff. Okay, that's cool. Map expected to be pointer. What is expected to be pointer? Argument 0 is expected to be pointer. Oh shit, all of that has to be in a different order. Fuck. Alright, so let's put it like this. Boom. Stack-based languages, am I right? Right, so there we go. This is how I'm going to be reverting this stuff. Okay, so argument. So this one is not a pointer. Oh, map returns an integer. Okay, so I can actually do it like this then, hopefully. So if we try to simulate everything. Okay. So this operation didn't fail, right? We can even confirm that everything went okay. So I'm gonna do something like this. It's gonna be puts, and then I'm gonna take the global memory that we allocated, ptr, and I'm gonna just try to print it and see if it looks like a pointer, right? I just want to see if it looks like a pointer. Yeah, it kind of does look like a pointer. Okay. Cool. So now, when we push in the global memory, op push global memory. So essentially, what we have to do, we have to push the pointer relative to the global memory that we just allocated, right? Oh, and fuck. Okay, this is very important. The global memory is expected to be 0 initialized. Right, so after we did this entire stuff, what we have to do, we have to memset it. Luckily, in the standard library, we do have a function to memset stuff. Right, so here we have to provide the size. We know the size, it's a global memory capacity, where this is the size. And then we have to provide the value that we have to fill it with. So this is going to be 0, and then we take the simulation global memory and read it as a pointer, right? And then we memset it. Memset returns this pointer, so I don't think we need it, so I'm gonna just do drop. So this is quite important. So this is quite important. Okay, cool. op push global memory, right? op push global memory. Porth.py, let me find push. I think it's just called push mem in here.
So and what we're doing here, we take the memory buffer pointer, like a base pointer, and we append the operand. Okay, that's cool. Simulation global memory. I read the value out of that thing. I think it has to be a pointer, right? And then I take the simulation operand, p operand, and I read this thing as a value and I sum it up. And here is the pointer within the global memory buffer, which I want to push into the simulation stack, right? But before I can do that, I have to cast this entire thing into integer. I wonder if I have to do that, so let's actually check the type of this thing. Right, so what is it talking about? Oh yeah, I forgot to do plus. Okay. Forgot to do plus, and this is the pointer, so what I have to do here is just I have to cast it to integer. So it's integer, so everything's fine. Okay, go. So data stack overflow in... Oh, okay. Don't say anything. Everything's fine. I'm a professional software developer. I know what I'm doing. Okay, what is your name? And it asks us. Okay, so let's actually see if we can answer anything. All right, so I'm going to do port Alexei. And okay, so now it fails saying that at 8 is not implemented. So it's a basically simple intrinsic that reads 1 byte from the memory. So that's basically what we need to implement in here. So let's go ahead and implement that. So it fails at 1627, right? 1627. Oh boy. And as far as I know, on the stack, usually how do you read that? So it has a pointer, right? So we have to sim stack pop this thing, and since it's a pointer, we have to cast that to the pointer, right? And then we read that byte, and we have to push that byte back into here, right? Since it's an intrinsic, we don't have to increment it, and to be fair, this is basically it. So this is how you implement this entire intrinsic, I think. So let's go ahead and see if I can recompile the entire stuff. Can I type in the compilation mode? I'm curious. Yeah, so here's the problem with the compilation mode. You cannot type in that compilation mode. So you have to do it like that. Okay, Alexei. And okay, we can simulate name. That's actually pretty cool. So yeah. Hello, Alexei. Go. You can in fact put anything in here and it kind of works. Yep. That's pretty pog. Porth. Simulation mode can simulate examples name.porth now. There we go. I'm gonna push that right at the repo. Cool. So let me see. So I'm gonna take a look at the examples, and what other examples can we have? Quine. Did you guys know that I implemented Quine in Porth? Right. I in fact did it, so this is the Quine in Porth. I actually didn't stream it, but it is legit. It can actually print itself. If you never heard about Quine, I really recommend to check it out. So it's essentially a program that can print its own source code, right? And if you think it's easy to implement, just try to implement it yourself. Right. Trivial situations are relatively easy to implement. You can just do the empty file trick or use the language that just has a command that prints itself, sure. But if you're up to a challenge, you can do that properly and just try to do something like this. You'll quickly run into a problem that while trying to print its own source code, you introduce more code that you need to print, which in turn introduces more code which you need to print, and you sort of go into this like infinite loop. And it becomes very difficult to break out of that loop and actually implement Quine. So this is a very good exercise. In fact, after I implemented a self-hosted compiler, I would say that self-hosted compiler feels like implementing a Quine. In fact, I think Quines are an example of simplest self-hosted compiler. So it's a compiler
of the language with a single command. And that single command is print the source code of your own compiler. Right. So, and while implementing the compiler for that language, you're basically implementing Quine. So yeah, at least this is how I view Quines. Maybe some people view them differently, but anyway. So I'm gonna put the link in the description and in the chat for anyone who's interested. So yeah, where's my description? So Quine. Here's Quine. In fact, I'm gonna tell you a little secret. The name of the operation of the language that prints the source code of its own compiler is a question mark. Right. So actually, I think this language has multiple commands. Right. If something that is not a question mark, you just interpret it as it is. If something is a question mark, you just print your own source code. And that's basically how you implement it. And that's the compiler that basically compiles this source code. Right. So we can actually demonstrate how this, Quine works. Right. So I didn't want to create a separate window. I just wanted to do examples Quine. .porth, and I'm going to just compile it, I'm going to just run it. Okay, so after I run this program, it printed its own source code that we're going to save here, outporth, right? Yeah, there we go. And then we're going to take a div between the output of the Quine and the Quine itself. Oh, shit. Okay, so... Well, I mean, for that thing to be a proper Quine, right? For that thing to be a proper Quine, you kind of have to skip the output of the compiler itself, right? So you have to put like -s flag, right? Which suppresses all of the outputs and stuff like that. So out.porth. And then if you do the diff, where's the diff? Out.porth and examples Quine.porth, there is no difference between these things. Okay. So this is a Quine. Can we interpret the Quine? So let's actually find out. So let's simulate Quine, and I think we should be able to. Push sister. Okay, this one is interesting. So we're pushing C-style strings. Porth.porth. Push sister. So I think it's the same as pushing string, but instead of pushing like size and pointer, we only have to push the pointer. So that means I have to only do something like this. So I can copy paste the entire thing. Right, and in here, as you can see, we're pushing the size of the string. In case of the C strings, we don't need the size of the string because it's null terminated. Right, so what we have to do in here, I think, is just drop this entire value. Right, so let me see. So this is the pointer. Okay, I think this is the thing that we don't have to push. Right. Okay, so at the top of the stack we have an integer which we can just drop. Okay, so we're gonna just drop this thing, and we're only gonna push the pointer in here. All right, so hopefully we'll be able to do. Okay, here we interpreted the name. This is not what I wanted. Can I interpret the Quine? Okay, so the Quine requires writing into the memory. So this operation writes 64-bit number into the memory. Let me see, 1658, and let's go ahead and do that. 1658, so on this stack we're having a value that we need to write and the pointer, right? So if I do something like simulation stack pop on the data stack, I get the pointer. And then another one, and then I get an integer, so I'll have to swap them. So after the first one, I think I want to cast it to the pointer because that's what it is, right? And then after I pop them all, I just need to swap them. right? Let's take a look at the final result in here. So here I have a pointer and I have a value that I wanted to write. Okay, so after that I can just like write that value in here, right? And that's it. So I don't think we need to do anything else in here. We just like perform the operation and that's it. So that should be okay. That should be okay. Just thinking. So everything's fine. Everything's fine. Okay, so I keep actually doing the wrong thing in here. So now we need to implement reading from the memory as well. So that should be pretty straightforward because we already implemented that for 1 byte, right? So we might as well just copy paste the implementation for 8 bytes and just replace this entire thing with 64, right? So there we go. So maybe I'm gonna actually replace it with Quine now. Okay, so now, oh, it needs if star implementation. Okay, that's cool. Oh, as you can see, it already started to print things. Look at that. It already started to print things. So the only thing we need to implement in here is like if star 1457, 1457. And as far as I know, it's like it's not different from if, right? And even in Python, right? If I take a look at if star, yeah, there we go. So here's the simulation. Yeah. So essentially, if the operand is if or if star, we just do the same thing. So in our case, it's kind of difficult to express this kind of stuff. So I'm going to just copy paste the if implementation into if star. Okay, so now we need to implement writing single byte into the memory, 1636. And I think here I can already start copy pasting things around, right? Because it's pretty straightforward. So what was that? Writing 8, and where is the store 64? Right, so here is the store 64, and let me find store 8. And here I just can do like this. In fact, I can maybe straighten it up and straighten up this kind of stuff. So all of these operations are like pretty straightforward. Might as well just go ahead and copy paste implementations for all of these things, right? 16-bit, right? So here is just like 16. It's kind of difficult to mess it up, so maybe I should not try to do it like that. Well, let's not try to do it like that because I'm kind of... Well, we only need like 2 of these implementations for 32 bits, right? So here's the 32 bits, and store 16 for 32 here as well. 32. I hope I didn't make any mistakes here. So that's pretty much all of the memory access intrinsics, hopefully. Let's go ahead and see if it's gonna work. It worked. So yeah, we managed to simulate the Quine. Let me go through the memory access intrinsics one more time, just in case. So this is 18, 16, 16, 32, 32, 64, 64, and that's basically it. That is basically it. I'm not sure how I'm going to be implementing the argc, argv in env-p, so this one is going to be a huge pain in the ass. Though for the env-p, I would imagine that it's as simple as this, right? Because that's basically it. But for the argc and argv, the arguments, there is a little bit of arguments that are consumed by the compiler itself, right? So we'll have to keep track of how many arguments we consumed and give not consumed arguments to the simulated program, right? So this one is going to be very interesting to implement, I think. But apart from that, did we implement like everything? So we don't have a max in here yet, but yeah, we will soon, hopefully. So push local memory is not implemented, which is kind of weird, but anyway. Argument 0 sim push. So this one has to be cast to pointer. There we go. Expected integer. Well, I mean, it has to be integer, of course. Okay, so let me do a committee. Porth simulation mode can simulate examples quine porth. All right, so let me see. Can we already simulate ourselves? Right? Do we really need everything to simulate things? Yeah, we do. We need argc and argv at least, and probably a shit ton of different syscalls and whatnot. I want to make a small break, super quick, and after the break we're gonna try to continue. And the goal of today's stream is to actually make the compiler to simulate itself. Right? That's the main goal. If we can manage to do that, that'll be actually pretty powerful. Not gonna lie. Right, let's make a small break and... Alright, let's continue the implementation of our nation. Oh. Okay, so what's gonna be the next thing that we have to implement? I have to interpret. We have FizzBuzz. So, how about that? Let's try to interpret FizzBuzz. I feel like it will be able to interpret FizzBuzz without any problems. Right, because I didn't see anything special in here, so I think it will be able to interpret FizzBuzz. Yes, it is possible to implement FizzBuzz in our language, so that language can already be used for coding interviews, right? Which is already pretty powerful. So FizzBuzz porth. Okay. So. Is it simulating? Yeah, there we go. So I think it went really well. I think we should try to simulate porth with itself, right? So I think the time has come. Let's see what needs to be implemented in here. Okay. Could not open file... Well, because there's no such file, obviously. I'm a dummy. argv is not implemented. Okay, so this one is a little bit sus. This one is a little bit sus. The problem is, the way our parser works, it actually stores the argv into a separate variable, and it advances that variable. So what we need to do, we need to get the access to that specific variable and use that. Okay, here we go. That's basically what's going on. So we have args, right? And we save the current argv into args. And then as we consume the arguments, right? As we consume the arguments, we basically advance that pointer. And in argv intrinsic, we just have to get the value of args. So to be able to do that, I think what we have to do, we have to make this shit global. That's what we have to do. Right. So, and proc simulate, I'm gonna put this thing in here, right? So this entire thing becomes global, right? And the main function consumes some arguments, but the rest of the arguments are available here for the simulation, right? So this is the rest of the arguments. So let's go. I'm gonna take args and I'm gonna read the pointer out of it, and I'm gonna put that into the simulation stack. So this is gonna be push. And I think that's it. Do we need to do anything else in here? I don't think so. So yes. So the only problem is argc now. Essentially, every time we consume a bit of args, we have to decrement argc as well. Right, and then use the decremented argc for the implementation of intrinsic. So that means we'll have to keep track of more things than I expected. Okay, so this is going to be push, and we have to cast it to the integer, right? Okay. So now it will complain about, okay, so it complains about push local memory. Oh shit, it probably doesn't need argc for the compiler because we don't use it. Okay, the compiler doesn't use argc. That's the point. That's pretty cool. So that means we don't have to implement argc for the compiler to be able to interpret itself. That's actually pretty cool. Okay, anyway, so here's the local memory. How do we interpret the local memory? Def simulate little endian. Push local mem. So what we do, we take a local memory RSP and we add operand. Okay, makes sense. Simulation local memory RSP. We read the value out of that thing. Well, we probably have to read it as a pointer, but I mean, whatever. Then we take the simulation OP operand, right? We read it as an integer, we sum it up, and we get the pointer that we have to push onto the simulation stack, right? Stack push, and I'm gonna cast it to integer because push expects integer, and then we also have to do sim AP increment 64, right? Because this is not an intrinsic. It's an operation of our nation. Okay, so that seems to be right. Do we need anything else? Do we need anything else? Yo, bro. It partially simulated itself. So it simulated itself enough to print its own usage. That's actually pretty cool. So it still needs syscall 1, right? So it wants to have a syscall 1. Okay. So let me copy paste this entire thing. Syscall 1. And a syscall 1 essentially, we're just gonna have that. Right, so this is gonna be just 1. This is gonna be just 1. There we go. So I'm gonna copy paste the same code to all of the syscall implementations. All right. Not enough argument for provided for syscall. Ah shit! Fuck! Damn! Shit! Fuck! Damn! All right. So we'll have to take these two things in here, and this is gonna be syscall 1. Okay, looks fine. Do we need anything else? Almost there. Okay. Would you look at that? Is that it? Is that everything that we need to have in here? Okay, so here's the port. I simulate port with itself. Okay, that's very interesting. Okay. So it took some time to compile the program. But can I now simulate? Holy shit. So I simulated port with itself, and the simulated version said that I didn't provide file to simulate. Now I can simulate the hello world. Okay, so for the hello world, for simulation of the other things, we have to have syscall 4. Okay, let's go ahead and implement syscall 4. So let me see, syscall 4. For the syscall 4, we have to have 5 of those things, right? So this is the syscall 4. So this is going to be 5. This is going to be 5. And this is going to be 4. Oh, right. So let me try to do this thing. So the port assumes argv is null terminated. I wonder if that's defined by the standard. I think I heard somewhere on the internet that POSIX kind of says that it has to be null terminated. Kinda? Sorta? Somewhere? I don't know. We need to double check that. Okay, syscall 2. Let's also implement syscall 2. So for the syscall 2, we just have to have 3 of them. So I can just like use... so this is 5. So this is going to be 3. I'm going to remove this thing, and I'm going to remove this thing. Syscall 2. Let's recompile this thing. The man page says, okay, so man page won't lie. Syscall 6. Okay, so I suppose we have to implement all of the syscalls. Let's just go ahead and implement all of the syscalls. Why not? Syscall 0 was the easiest one to implement. Look at that. Because it doesn't like it expects one thing on the stack, so it's pretty straightforward. So syscall 5. Okay, so this is the syscall 5. It expects 6 elements on the stack. Right, so here's that one, and here is the 6th one. And for that one, we're going to have 7 of them. The art of getting shit done. The art of getting shit done. Don't judge me, chat. I'm getting the shit done. Wait, okay, so this one is syscall 6, right? This one is syscall 5. This is the 4th one, 3rd one, and there we go. So here are all of the syscalls. Do we need anything else? Okay, let's try to simulate this thing. Holy fuck, it is slow. Okay, so maybe something is wrong in here and I forgot to do +1 somewhere, I'm not sure. But it feels like it's stuck. That's what it feels like. Wait a second. Alright, so it expects the input file, but it couldn't do shit. So let me see. Okay. I wonder if it's doing anything, or is it just that slow? Strace it. That's like actually a good idea. We can try to strace it maybe, just to see what's going on there. Well, I mean, yeah, it only goes not that deep. It doesn't really go that deep, so it does not strace some of the other things. Okay, so for this stuff, did I forget? Like for this, for the intrinsics, we don't have to do +1, right? We just don't have to do that. All right, so let's actually try something simple. Right, let's try something simple. How about foo porth that takes 69 and just prints that thing, right? So we can try to simulate foo.porth, right? And could not allocate 0 bytes of global memory of the simulation. I'm really glad that I decided to handle the output of mmap. Who would have thought that you can't allocate 0 bytes of global memory? Did you guys know that you cannot do that? I didn't fucking know that. So let me try to do that. Could not allocate. We can do something like, I don't know. So global memory capacity, right? We're gonna read this entire thing, and only if it's greater than 0, only then we can try to, you know, allocate some shit. Right, I think it does make sense, right? Don't try to allocate it if it's, right, not available. Because some of the programs don't have any global memory, so what's the point? Wait a second, I think I'm being stupid. Yeah, I have to put it like this, even. I would even say like this. Yeah, that's right. So, like this entire stuff. All of these separations have to be under the condition. Under the condition. Here we go. We're almost there. It's just like really unclear what's hanging in there. Okay, so here's the 69. Nothing special. So then we can do port. So then we provide the simulation, and it says no inputs provided for the sim subcommand. And then if we try to do something like this. Okay, so that was pretty cool. So if I try to include the standard library, maybe the standard library, the compilation of standard library is super slow. Maybe that's the point. So if I try to include std_porth, maybe that's what slows everything down. Probably. That's probably what's going on. So we're simulating the simulation. Python speed. We finally reached the Python speed. Finally. My god. That's very weird that I cannot just like simulate that shit. Though I can simulate it without this stuff. Like, I don't know if there is a bug in the simulation or it's just that slow. That's the problem. Like, I don't know. I really don't. Simulate, 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 simulate. Maybe it is that slow. Who knows? So let me take a look at some of this stuff, at the diff specifically. So this is just a memory, nothing special. So push local memory, I do increment sim IP. All right, so, no, it's an intrinsic, okay, so that's fine. argv is fine, syscall1, so everything that is intrinsic, it is totally fine to not increment by 1. Okay. So let me think what we can do to actually confirm that this thing is just being slow. What can we do? Because if I start sticking simulation into this thing, well, okay, so we can try to just log what's going on. Why not? So proc simulate, here it is. Let's try to simulate this thing. So here is the OP. Okay, that's cool. So I take the simulation OP and I take the token where it's originated, that OP. Then I take the token location, right? So I add the location and I'm going to print that location. So it's going to be put lock, right? So, well, that will slow it down even further, right? So, but with this, maybe we're going to see if it's stuck somewhere, right? So maybe that's something that we can do. And in here, we can just print the operation, right? And do we even have anything like for converting operations into strings? OP as OP type as, oh, there we go. So we have that. So I can just take sim OP type plus and read this entire thing, and then I can say OP type as a string, and then I can print this thing and then the new line. There we go. So this is going to be something like that, right? So then like this, then like this, and there we go. So we're just printing it. So we're basically tracing the operations that we're currently interpreting. Right, so I'm going to try to compile the entire thing. Right, so I'm recompiling the compiler. And I'm going to try to simulate the 69 example, but I'm going to not include this thing. So I'm simulating full porth. Right, as you can see here, we have full porth, push integer, and then intrinsic. So basically tracing this entire thing. If I try to simulate porth.porth, the amount of operations here is going to be way bigger. So here are all of the, here's all of the operations that we simulated. That was kind of weird because it didn't print them right away, if you know what I'm talking about, right? So it waited a little bit for whatever reason. So let me try to simulate it maybe in here. So that should be pretty straightforward. Okay, so that's fine. Let me see. So if I try to now simulate the compiler with itself, right? So this is going to be foo.porth, and well, that kind of, okay, so that worked and it finished, right? So that worked and it finished. So if I try to simulate this thing now, if I try to simulate this thing now, is it repeating itself? You out-commented std. Yeah, so I have to actually bring it back. So let's simulate. I'm actually a little bit tired. Skip procs, everything seems to be fine. Port.porth. Let me. I'm really tired. I can't think anymore. But to some extent, what if we try to compile it with itself? Right. So if I try to simulate this thing, right, and then I hit the compile, can I at least compile, you know, a simple program? Can I at least compile a simple program? Okay, can I at least compile a simple program? And let's just... I can't think anymore. Alright, so this is gonna be like that. Alright. The fuck? So, but one layer of simulation works. I think I'm gonna follow the consensus of that it works, it's just being super slow. Right, because that simple example works perfectly. Right, this simple example works absolutely perfectly. So we're simulating the compiler, which simulates the program, and the program is being super simple, and that works. So the simulation of the simulation. So yeah. And how fast it is? Because simulating something more complicated may require like a lot of like you have to simulate like the whole machinery of the compiler actually. Compare it to Python. Python is gonna be faster, by the way. Right, if I just do Python porth.py, yeah, so it's definitely gonna be faster. Yeah, there we go. So it's 8 times slow. All right, so I think today was a pretty good progress, I would say. We're finally able to make the compiler to simulate itself to some extent, right? So let's do something like porth.porth, and let me see, how should I call that? The compiler can kinda simulate itself, but it's super slow. It's super slow. There we go. And I'm gonna push that right into the repo. Right. Does anyone have any questions? Does anyone have any questions? So before I go. Oh my god, Matthews F777, thank you so much for 35 months. That's a lot actually. Thank you so much for 35 months of tier 1 subscription. That's a lot of months, holy shit. And welcome back to our Epic Porth Club, the real OG of the channel. Thank you so much for sticking for so long. Thank you. I'm really glad that still there are people who've been around for this long, no matter what it is. I do not deserve you guys, really. Thank you so much.
All right, so today was an interesting stream, at least for myself. Right, we implemented this simulation. I still don't really know if it's just that slow. Yeah, okay, so you know what I'm gonna do off screen? I'm gonna actually leave this example, right? So basically simulating the compiler with itself and trying to simulate something with a standard library. I'm gonna just leave it for like an hour or maybe 2 hours and just see if it's gonna ever finish, right? So, and yeah, we'll see. Right, that's it for today. Thanks everyone who's watching me right now. I really appreciate it. Have a good one, and I see you all next time. I don't know what's gonna be next time, right? So I still haven't decided. Usually I just like continue developing Porth, and if I see something interesting, I basically schedule that for the stream. So far I don't really know what could be the next topic. We'll see. The winner gets tea, that's for sure. In any case, thank you everyone for watching. I gotta go. Love you all.